Welcome, and of course, Happy New Year, everyone. Welcome to the number 60 of the Epic Online Technology Meetings, second chapter of Season 3. Wow, that's the only way to describe why ultrafast lasers are getting such huge traction across a growing number of important applications. An initial boom in biotechnology and micromachining caught the eye of the full industry. Now, femtosecond, picosecond, and nanosecond lasers are established as stable, mature, and reliable, offering high quality and quantity. But this meeting is not a technology push. I want to hear about real-world applications. My VIP list on January 13th looks like the credits on an epic motion picture. Look at the big players like the Finnish Outokumpu. They are the masters of stainless steel. Others like Marelli are making and delivering next generation automotive lighting. And I'm sure that, like me, you are curious about what famous names like Ferrari, Maserati, or Lamborghini are doing in the field of advanced laser manufacturing. What about semiconductor companies like Infineon, consumer good manufacturers like Bosch or Huawei, leading optics companies like Leica or Zeiss? They all need and want customized ultrafast lasers. So let's discover the pulse duration, frequency, and beam shape specifications that matches their needs. And looking beyond material processing, remember the Large Hadron Collider at CERN depends on femtosecond lasers to maintain synchronization across the entire macro system. So plenty of reasons to put Wednesday, January 13th, 2021 at the top of your New Year agenda. Join in the conversations with leading experts. So just sign up to participate in our Zoom room to put your company logo on our wall of fame, or watch it in real time or anytime at the Epic YouTube channel. See you on Lucky 13th at 3. Wow. So see you here on Lucky 13th at 3 and 2 minutes. Let's start with a fantastic meeting. And first of all, I would like to thank all the hard work that my colleague, Dr. Francesca Moglia, has put over the holidays to have a fantastic supply chain at the meeting. Epic keeps growing. I heard today we received the application from companies like Fujifilm and Adva. We are almost 660 members, and we keep growing with the large companies and the small startups try to make the connection. Thank you very much for all the support. And also keep growing in the staff. I want to welcome Tracy. She's going to be our market analysis expert, Photonics research head of Photonics research expert. And we want to provide more value to the membership in the sense of market reports, more events, the bigger website to find a job in Photonics, jobsinphotonics.com. And of course, what makes us unique, the network, connecting companies. Tell us which companies you want to connect. And as I said before, today is the second meeting of the season 3 of the Epic Online Technology Meetings. Today we talk about laser applications on ultrafast and high power lasers. If you are interested in any of the upcoming meetings, the list is public. All you have to do is register online. Please remember to register online. And also I would like to announce that this year we are also supporting quantum technologies. So for those of you who have an interest, an application, or a potential use of quantum technologies, or just share my passion, which is quantum, sign up for any of the upcoming quantum technology meetings. And that's all. Let's talk now about Francesca's passion, ultra-fast and high-power lasers and their applications. I would like to first of all acknowledge the support of our media partner, PhotonicsViews and AZO Optics. Thank you very much for your continued support. And this meeting could not be possible without the support of our sponsors today. We go first to Lithuania, Optoman. If you're looking for laser optics and IBS coatings for laser optics, for high fluence or for high power applications, for ultra fast applications, Optoman is your partner of choice. If you're looking for an autocorrelator or any way of stretching the pulse, characterizing any laser pulse, APE is the partner of choice. Asphericon, spherical freeform, any optics with high demand for dimensions. Asphericon is your company to select, and all the way from Jena, we're going to hear later from Sabrina about this. If we want to go to the company that can actually manufacture lasers, lithium lasers, an Italian company that manufactures highly customized, high-power femtosecond lasers with repetition rates that go from 40 megahertz to 1 kilohertz. And if you want to hear about semiconductor lasers, you go to Finland, you go to Tampere, and you talk to Modulight. Modulight specializes in semiconductor laser manufacturing. They do their own MBE growth, and they go all the way to providing their lasers to clinicians at the clinic. And we go also to Zemax, and Zemax is for all the optical designers. I've been a user of Zemax. It's the best software you can do for optical design. Thank you, Zemax, for supporting this meeting. Fluence, all the way from Warsaw. Cześć. Fluence lasers are the answer to the high demand for reliable turnkey sources. Thanks to the unique all-fiber construction and not using degradable components like CSAN, Fluence lasers feature double free operation and excellent lifetime and fantastic max. And we finish with Prospective. If you are looking for a laser solution for this market and you're looking for having the best potential beam shape out of that laser, you have to contact Prospective and make sure that you have the entire value chain around it. Thank you very much, all the sponsors, but a special thanks, grazie mille, to the epic expert in charge of this fantastic meeting, Dr. Moglia. Thank you very much for all your hard work. What's in the menu today?
Thanks a lot, Jose, for the nice introduction and for introducing this great meeting. So as you see here, this is the boring way of showing our agenda. That means only the speakers in a list and not mentioning all of you that are actually here now that are already seen, more than 60, great. So here is the way we try to represent you all. So these represent all the people who sign up for this meeting. So thanks a lot for this. As you see, we talk about high power and ultra fast lasers, and we have a few end users here today. Some will have a few slides, some will just be here and listening to us and maybe also propose what are their challenges at the moment in the field of high power ultra fast lasers. And then of course we go on to the laser system integrators. We have really many also here today, very nice, and that are really thinking about how to integrate the next generation of ultra fast lasers for also different applications. Then laser manufacturers, we are really happy. We hope we are really all there, because it's really good that you appreciated these meetings, that you all join to see and to tell us also what are your latest discoveries and developments. So thank you. And then for the real next discoveries, R&D. So we have many representation here. And then the full supply chain. I don't stop to talk about everything, but of course for ultrafast laser we need optics and beam shaping. Packaging and testing is also in assembly are really important. We have many also pulse stretching, so pulse management is also important, thermal management. So we have all covered, and I guess hopefully we will have nice discussions and to tackle some challenges today.
Grazie mille, Dr. Francesca. I have to say that this slide only represents the companies who registered for this meeting. So if you are an EPIC member or you're missing your logo on this slide and your logo is here, we didn't forget about you. Just please remember to register if you find any of the online technology meetings suitable for your technology. Francesca, a meeting with Tata Steel, a meeting with Marelli, a meeting with ABB, with Thales. Great job. Fantastic job. This meeting is also broadcasted live in YouTube. So I'm going to say hello to the YouTubers. Hello, YouTubers. If you want to get in touch with any of the participants today, the participant list is really at the YouTube page. You just have to click there. Just send me an email and I will make sure I make that introduction. And this is, of course, also valid for the people in the Zoom room. Remember, there is an internal chat. Use it to connect to each other and do business. But then, if you don't manage to have the right connection after the meeting, send me an email with the companies that you want to interact with, and I will make individual introductions because I love doing that, because that's really my passion. And today we're going to start the meeting now when we had the first speaker, an end user in the steel industry. Pieter Baart, principal researcher at Tata Steel, is going to kick off the meeting today. Pieter, thank you very much. Thank you very much for being with us today. The floor and the attention of everyone in YouTube, in the Zoom channel, all over the world, goes to Tata Steel, goes to you.
Thank you. I'm sharing my screen. Welcome, everybody. My screen is visible.
Crystal clear.
Yes. Well, my name is Pieter Baart. I'm a researcher at Tata Steel R&D in the Netherlands. And today I will present you my most exciting project. what we want to do in this project is use your equipment, lasers, to texture the surface of steel, basically a full coil, which you see in the image here. And that's thousands of square meters of surface. So that's quite an ambition to do this. We cannot do it today. And for that reason, I will present you the challenges which I see and or support us to realize this in the future. So let's see what we want to do. Now, so we want to use laser to apply a texture on the surface. We have been looking together with the University of Twente in the Netherlands on creating these kind of dimple patterns on zinc-coated steel using nanosecond and picosecond lasers. In the next step, we have also looked with one of you on larger size samples, such that we can really demonstrate internally, but also to other people, the functional surface properties which we can realize by using this technology. And maybe I should put this one down. And then in the next step, we have also did some tests where we created tailored surface textures, as we call it, where you don't texture the whole steel plate with the same type of texture, but you can really optimize locally to drawing process customers, for example. So this is all great, but how do we do it today? Maybe it's good to give you an idea of the starting point. So here you see a hot dip galvanizing line, a schematic picture, and on this kind of line, we produce galvanized material a lot for the automotive industry. So that's high strength structural steels for the frame of the car, but also high surface quality steel for the outer panels of the car body. Especially the surface finishing is really, really important. In this production line, there are a few steps. There is a heat treatment section, there is a galvanizing section, and there is a surface finishing section, which mainly consists of the temper mill. And this is what I want to look into. This temper mill, which we use today, has a number of objectives. First of all, to improve the mechanical properties of the steel itself. It does some shape control, but for us most important, it creates the strip surface texture. So it basically copies it presses it into the steel strip, which is flying through with a speed of 2.5 meters per second. And my ambition is to realize a process here where we split the mill step with the for the mechanical properties and the surface texturing by doing that with laser. So this is not something we can do today. This is quite challenging. I have identified a number of challenges which I want to share with you. And that includes, first of all, the process speed itself. So if you look at the beam delivery beam, which is scanning over the surface, depending on the pulse duration we use, we are limited in the beam velocity. At the moment, I'm mainly looking at nanosecond pulse duration. And then you have to remember the speed is also going at the strip is also going at quite substantial speed, 2.5 meters per second. So that means with one single laser beam, you will see a kind of drift in the surface, and you really need a number of laser beams to create a full coverage of the surface with these kind of beam speeds. And then second is, we can quite easily make a deterministic pattern on the strip with the kind of scanners which are available today. But what we are aiming at, in fact, is something which has a kind of randomized component in it, because we are afraid that if we have a too well organized deterministic pattern, that you can get this kind of moire effects. So that's, for example, the interference with pixels of a camera, which you see in the right top photograph, where you get this kind of interference patterns with our definitely not. And then the most challenging thing will definitely be the system integration. I have done some calculations. What do we need to apply this technology in our hot dip galvanizing line? Well, we need about 380 kilowatt pulse laser output power. That's amazing. And at the same time, we need 2,000 to 3,000 parallel laser beams to cover the top and bottom side of the steel strip, which is about 1.5 to 2 meters wide, which moves by at a velocity of meters per second. So that's really an ambitious target, which we can definitely not do in one step. So that's why I created a kind of roadmap. Today we are in a situation where in a lab environment, we have realized strip properties, we have looked at the feasibility, where is the state of the technology now, what steps are required to go to these hot dip galvanizing line type of applications. But on the short term, I see a kind of where we will do single blade. So we have a kind of batch production technology where we have square meters which we can apply texture on. Locally optimized textures to support the deep drawing processes of our customers as well. And then in the medium term, we can do this in a continuous process, in a full coil, but at a rather low speed. We can have a dedicated line to do this. And then in the long term, we get back to our hot dip galvanizing line of meter second speed. So we need to do about 4 square meters of strip per second with the laser. But that will definitely not be today, not tomorrow. But that will take a couple of years, and I really hope you can support me in realizing this. So that's what I wanted to show to you today.
Thanks a lot, Pieter. Thanks a lot for being here today and bringing your wish list. So if you remember when we had our first discussion, I was saying, wow, this is really a wish list, the special one for EPIC members and not so present here. So it's really nice. Also looking at the future of the future is good. So Pieter today really presented something that is not be done today, but also in a while. So all guys think about it. If there are some questions to Pieter, because you said already a bit, you didn't summarize all together, but basically we always ask what can you do for them and what can they do for you, but you are basically looking for something really on large surfaces, many beams, high power, very high, I would say. And you were talking about the nanosecond laser. You said we were having a chat. It could be, of course, also picosecond, we said, but it would be also even more demanding. But if someone wants to comment on this, feel free. So I see that there is already a hand raised by NTS Optel. So if you can say your question also live, so you switch on your microphone, you can tell it yourself.
Yeah, Pieter,
Frank.
Hi, Pieter. What can the laser do, in your opinion, what you cannot do today? I think you have that roller before, and why do you want to switch to this huge laser system? Because the benefit is not clear to me.
Yeah, there are a couple of things. On one side, it is the process stability, or the process production line. We process a lot of different type of materials, which also means that sometimes we need to press harder, sometimes we have to press less hard. We use different type of work rolls with different kind of surface textures or patterns, to be able to also create some roughness on textures in very hard steels. So this is, from a production point of view, really a nightmare today to organize this in a logistical way. And we also see great benefits for our and really tailor the surface texture to the specific location of their product. So now we make a product which has the same surface over the whole width of the steel and the whole length of the steel. And what we really want to achieve is something where the customer tells us, I want to make this type of product. I put a picture of a car door in my presentation, and we can, together with the customer, locally optimize the texture for deep drawing purposes, for paint visibility, all those kind of things.
Okay, yeah, clear. Thank you.
So Frankie, do you maybe want to mention what NTS Optel is doing so that all the others know as well? We are many people today. Just one sentence about it.
Yeah, of course. NTS is a first-tier supplier that and acts as a system integrator to help customers, solving their problems basically, and then I represent basically the optical group. So maybe we can indeed help Pieter, but we do not supply these lasers. So we would basically more integrate it in a total system.
That is also very useful. So thanks a lot, Frank. So now we have a few hands raised. So first, Kevin from EdgeWave, right? You can ask your question.
Yes, I already write in the chat.
Yeah, but we want you to speak.
For me, it's a very interesting challenge application. I mean, we are a laser maker. We provide such laser for also similar different applications. That's why my question is, what kind of structure you prefer? Means the diameter of the structures and depth of the structures. And also, I mean, you are using nanocycle laser. You have some melting on the surface around the structure, and this is okay for you because you are looking for steels for application or high-end application like the surface, side surface is important. So, and the next one, I mean, this kind of direct engraving process, I mean, this is very challenging, and the economic way is even more challenge. And but what do you think about embossing process? Means you have a cylinder with structure you want, and just engrave or just pressing this kind of transfer this kind of structure on your metal sheet.
Yeah, this embossing process is what we use today, with having this kind of the negative or the counterpart of the structure on a roll, which we press into the steel, but that has the limitations which I just explained. So doing it directly on the steel strip gives us much more flexibility, also in production, but also opportunities for our customers. Mm-hmm. The type of structures we are aiming at this moment is this kind of dimple type structures. Our customers are used to certain roughness levels. The roughness itself doesn't say anything about the structure, of course, mm-hmm. But to be a bit in the same range as they are used to, I'm aiming at dimples which have a depth in the order of 1 to 3 micrometers. And a diameter in the range of 30 to 60, maybe 100 micrometers. Mm-hmm. And the nanosecond pulsed laser is what we look into at the moment, mostly because of cost. I mean, these type of lasers are available at relatively high power output. For picosecond laser, that's a different story. And also what we found for picosecond laser, which has the advantage, of course, of not having the rim or the edge around the crater, but you will need multiple pulses at exactly the same location to create the depth we are aiming at. And that we also see as a big challenge. So from a laser point of view, we see that there are offerings in the market which to some extent fit, maybe not yet the 380 kilowatts, but 5 kilowatt is available. Okay. But for the beam delivery and the alignment of the optics, that's much more challenging, I would say. Okay. Thank you for the question.
I'm not sure if I have one more question.
Maybe we have a lot of raised hands.
Sorry. Okay.
Because of course we can put you in contact any moment, also after this meeting and offline, online. But I want to ask also first, and maybe later as well, we can pick you up again. Thank you.
It's fine.
So now it's time, I guess, for Michael from your IPG Photonics. I remember chronologically. If you want to ask your questions, you're welcome.
Thank you. Can you hear me?
Yes.
Great. Hi, Peter.
Hi.
Here's a bunch of laser companies, I guess, excited about this high power level. Do you know a house number, a break-even point for us on the CapEx for such an equipment where it makes sense to replace the conventional technology and use the laser sources, whoever it is and whoever it looks like? But we should have a certain house number for that.
Yeah, that's a fair question. And that's also where we have some difficulties. We see these advantages, but the cost involved with the prices today, they are beyond anything which would make sense for us, especially in a case where we have a production line already and we are replacing an existing platform which is there. I estimated things in the range of 20+ million euro, which we need to invest. And I have to be honest, today we are in a situation where the steel industry has little margin, and we have other investments which have a lot of attention related to the environment, CO2 emissions, etc. So I will not be able to have this money available this week. But I foresee in a couple of years' times, when there is a shift in focus on technology, but also how we can differentiate our products from competitors, etc., that there will become possibilities to do this kind of investments. I hope that answers the question.
Perfect. Thank you.
Thanks a lot. So talking about lasers of the future, maybe Tim from Fraunhofer AWS can say what he's doing now and what is maybe what can be done in 2 years. Tim.
Hey, everybody.
Hi.
So hi, Peter. So for sure, so I'm coming more from the application side. So I'm pretty sure there are a lot of people trying to fit the requirement for the kilowatt laser, so the number which you, let's say, pointed out. Did you ever looked into, so you mentioned some specification of the, let's say, texture which you are aiming for. Did you have some, do you looked into some interference-based methods? So you mentioned Moiré effect, so that you well-defined pattern usually maybe mix up some things. But did you ever look into some interference, let's say, processing? This, for instance, the world where I'm coming from, where I see, let's say, that you maybe in the end don't need so high laser power, so the demand is maybe not so high, but you could, let's say, reach these high processing speeds which you potentially, which you have in mind.
Yeah, I'm closely following the Lampas project, and I'm very much interested in this interference technology, the DLIP, which comes from you. The problem I see is that these are generally surface structure at a different length scale than I'm interested in. So I'm looking into tribological properties, friction properties, etc. And for that, these kind of bit more core structures look ideal. Nevertheless, and that's physically limited by the wavelengths of the laser, of course. We cannot infinitely scale up the size of these kind of structures using this interference technology.
Yeah, so maybe
I do see, but that's maybe another discussion. I also do see possibilities for that interference-based technology for use in our production processes.
Yeah. Maybe just as an add-on, let's say this, what you mentioned, the 30 to 40 micrometer, let's say, periodicity might be feasible. Of course, if you go to 100 micrometer, then this would be for sure challenging for an interference-based, unless, let's say, the laser system can deploy enough laser pulse energy, let's say, then maybe we can talk about that.
Yeah. Maybe good to have contact later on this subject.
Yeah, would be a pleasure, sure. Thanks.
This is just a starting point, and then the big work starts after this meeting. Thanks a lot. So now, last but not least, so Joachim from Pulsar Photonics, he has a question. He has a talk also later, but if you quickly can ask the question and then we go on. Thank you.
Yeah. Hello, thank you very much. Hello, Peter. Do you hear me?
Yes.
Yes.
Okay, I saw on one of your slides that you have quite a good agenda how to proceed with batch processing, slow speed, and acceleration afterwards. And as well, I saw a slide where you have a small future look to the system technology should be used. I saw polygonic scanning and AOM system as well. Do you have an agenda how to couple all these available technologies, thinking about beam splitting, fast deflection system with AOM, polygonic, multi-beam, whatever else? How is your agenda to put these all close together? Because I guess if you're talking about such huge laser powers, you have nearly to apply all of them.
Yeah, good question. So far, I've spoken with some laser suppliers, part suppliers, etc. So I have a brief idea of what, say, the current optics are capable of dealing with from a laser power point of view, and that's not enough. I mean, if we want to do something, I foresee that we need to process around 70 of these laser beams through one polygon scanner. So 70 laser beams at the same time. And then with a pulse energy in each beam, that's quite substantial amount of power. I think currently these kind of polygon scanners are not capable of doing so. Simply the optics are not capable of handling this amount of power, but then also the randomization part and having these kind of parallel beams aligned to each other, that's a completely different challenge which needs to be solved as well. And I do not have a detailed roadmap on how to develop all these different components and integrate them together. But that is something which in time will need to come. I think we really need to take this step by step. But today I wanted to present to you my very far future ambition. And
do you have a project name for it?
We can make a few steps.
Do you have a project name for that?
Peter, did you get the question if you have a name for the project? It's the hysterical name, probably, because I see a lot of people smiling.
Yeah.
It's more like an hysterical smile, because the challenges here are beyond beyond the line, but that's why we are here. So we are doing the industry of the next years, so not only the one of tomorrow. And so I would say, Peter, you are open for calls, right? So I imagine everybody can talk to you, because I guess many here maybe are still silent because they're thinking about it, but there are for sure room for collaborations with the full supply chain today. So thanks a lot, Peter. Don't leave, because we will maybe pick you up later with some other questions, because as we saw, there are some multiple questions coming. But now it's better if we go further with the agenda. So it's now time for Paulius. Right. So we go back to a bit to the R&D phase. So let's see if Paulius says something for you. Very maybe specific, not, but let's see. Paulius, are you there?
Yes.
Yeah, and the slides are coming. The floor is yours.
Yes, thank you. Thank you for introduction. Okay. So I'm Paulius Gečys, so I present FTMC and Laser Microfabrication Lab. And I will just briefly talk about what we are doing in our lab in the case of copper and steel milling with ultra-short pulse lasers. So modern ultra-short pulse lasers usually have high powers, have high repetition rates, but also we have some interesting features like a burst regime, so where a single pulse can be burst into smaller pulses spaced in some really short time, for in this case, for example, 15 nanoseconds, which represents 64 megahertz burst. Also, these lasers can do even gigahertz bursts. That means the distance between these pulses is even shorter, for example, like 200 picoseconds. And it's also interesting that these new lasers has also features we can do burst in a burst. That means you have like multiple pulses in a gigahertz burst, in a megahertz burst. It's even different to explain, but it's really easy to see in the image. So as you see, there are a lot of parameters that you need to take into account when you want to optimize, for example, milling of metals, copper or steel. And you want, of course, these lasers are expensive and every photon counts. That means you need to use your photons efficiently. So we did a lot of research in this field. So besides these all burst modes and so on, you also need to take into account that you need to optimize the laser fluence for each different parameter sets, for example, for different burst regimes. So there are a lot of variables in your equation, and all of this you need to take into account and optimize to achieve the best efficient process. And what is the most important, if you work on this optimized regime in an optimal fluence level, you have the highest efficiency. That means you have the highest material removal rate in cubic millimeters per joule per minute per watt. And you also have this really the highest surface quality as well. So this is really important things to do, and our lab spend a lot of time in researching these mechanisms. So here some efficiencies for copper and for stainless steel we reached, and I can tell that, let's say, for crater drilling, some of the efficiencies are higher compared for milling of cavities. For example, the highest efficiency we reached today was like 8.8 cubic micrometers per joule for copper drilling in a megahertz burst megahertz with 3 pulses. It was in the case of copper cavity milling, we reach a little bit lower efficiencies, but they are, let's say, higher compared to a single pulse conventional milling. And what I can say, these milling efficiencies are like a world record top efficiencies, because we try to optimize these burst regimes together with the fluence optimizations, which gives the best optimal results. In the case of gigahertz burst processing or B-burst processing, so we were not such successful in breaking world record efficiencies, since well, our laser had only like 25 pulses per burst, and this is just was not enough for this gigahertz burst to boost efficiency in a gigahertz regime. Yeah, so we apply this. You see some pictures of our milled features in copper and stainless steels, and fine features, and this is what our lab is developing. And yeah, so if you need some process developing or some advices, you can always contact me. And thank you for it.
Thank you very much, Paulius. Acho, Paulius, thank you very much for being in this meeting. Actually, I have seen the laser microfabrication lab in Vilnius when I could travel, when I was traveling 200 days a year, and I loved it. And it's an experience that I recommend everyone. Paulius, this is an epic meeting. And you know what that means? There are 650 companies that want to work with you. What can you do for them? And what can they do for you? What collaboration opportunities do you expect after this?
Yeah, so actually we are process develop, so we do process development. So if you have some applications where you need to test, and then we have a lot of we have lasers, we have our instruments. We can do some research, R&D research for you if you are interested in such things.
Paulius, you mentioned some interesting laser from light conversion, which I'm actually a fan of, and I would like to say also a show for them. Really, really great femtosecond laser regime. I want to ask you about laser pulse characterization. There are many femtosecond laser companies today in the room and others, and we want to compare apples with apples. How do you currently characterize, how do you currently measure the pulse shape?
We actually we are more like a laser application lab. So
you know
this
the
characterization
magic
for the laser manufacturer.
You know the magic of these meetings? I have everyone in the room, so I can go to APE. Do I have anybody from APE? These fantastic autocorrelators. When I do like this, everybody knows APE. Mateusz, Ibek from APE. How are you doing this afternoon?
Thank you.
Yes, I think here you are. Yes, I am very, very interested in knowing if there is a standard process to characterize the pulse shape in these femtosecond lasers. I know APE has developed the autocorrelator that everybody is using, and I love using it. How do you address this challenge?
So I think the most common and most used method is autocorrelation. We get roughly the pulse duration of a pulse. There's more sophisticated methods such as frog or spider, where you can really extract or measure the real pulse duration. And I think that's the most common methods used in R&D or in monitoring of laser pulses. There's also different or more sophisticated methods for the autocorrelation. And if I may, I would like to show you one slide of a high contrast autocorrelator, where you can see, I think it will be a little bit surprising for most people, how a pulse looks like. So
yes, please show us.
Let me share my screen, and now I have to find it.
It wouldn't be an ultra-fast laser meeting without the autocorrelator of APE, so we need to see it.
So, do you see it?
I will. Yes, here it is.
I don't see it myself.
We see
sorry for the technical issues.
We see a pulse in time from 0 to 1,000 picoseconds.
Yes, so this is a roughly 200 femtosecond laser, fiber laser, and you see this peak, this very short peak, and this is the specified laser pulse duration. But what you normally don't see, and what normally nobody measures, is the rest of it. So it looks like the Swiss Alps, and it goes around to 400 picoseconds, and this is what the power meter sees. So if you do a power meter measurement, you will see 1 watt, but it is not compressed in this pulse. It stretches to even 800 picoseconds outside of the pulse. This is not, of course, not much power sometimes, but sometimes it's also a lot power, and is doing, for example, like having effects on the heat affected zone, and then, for example, eye surgery. It's very, very important to reduce this kind of background or base to the minimum. I don't know how interesting this is for material.
Very interesting. You had the right audience for presenting this. We're going to come back to this point of measurement, but now I want to go to one of our end users in the room. I'm going to go to Infineon. Benjamin, a big fan of EPIC, I know. Benjamin, Happy New Year. What's on your mind?
Yeah, thank you very much. A very interesting talk. And since we are manufacturing a lot of copper, I mean, we have many applications where copper is inside. And you mentioning the world record efficiency, of course, I want to learn a little bit more about. And one question, you mentioned burst in a burst. I think this is pretty funny, and gigahertz burst applications, but do you really see there a qualitative benefit? Because I have learned that the gigahertz burst behaves like a nanosecond pulse. Can you comment on that?
Yeah. So actually, gigahertz burst. Actually, yes. So in a gigahertz regime, what you do, you actually control the thermal effects. You have really precision control of your thermal effects, and by that, then you can increase the efficiency. Of course, the quality will be lower compared to conventional processing with like femtosecond or picosecond laser. But still, it will be, you have benefits compared to nanosecond processing and with higher efficiencies. So this is the main advantage.
Okay. And you mentioned the efficiency in cubic micrometer per microjoule.
Yes.
And for us also throughput is a little bit important stuff. So we usually also need to have a time scale for that. I mean, are you able to use the UKP benefits and also do fast movements, or is it really a slow process where you always give the material time to relax and it's very,
no.
university kind of style?
What we are using usually is a Galvo scanner, so we can move really fast, meters per second, it's no problem. So we actually even have a polygon scanner as well, so we can increase scanning speed up to 100 meters per second. But so it's now, so the scanning equipment is not a problem. The problem is the laser, for example, for the polygon scanner. So you need quite powerful laser with high repetition rate. So to do machining, to have sufficient pulse overlap to do milling. So
okay.
Yeah.
We have two more questions in the room. Now we're going to go to...
One last question, Jose, please.
For Infineon anything. Benjamin, go ahead.
Thank you. You need to come and visit us one day, Jose, and also Francesca as well.
And also Paulius.
Invited. So if I send you a 300 millimeter wafer, are you able to do machining on that in your lab?
Yeah.
Okay,
yeah.
Good. Thank you.
Oh, that was a fantastic question. I'm happy to let you ask. I'm going to continue and I'm going to go to Italy for the next question. We go to lithium lasers. Alessandro, what's on your mind?
Thank you, Jose. No, I wanted to ask to Paulius, because he said that in order to increase the ablation rate in his experiment, he wanted to, I understood that he wanted to go above 25 pulses. So my question is your ablation rate limited by the number of pulses delivered by your laser source or not?
Yeah, so then actually you work in a gigahertz burst regime. So you need to have a lot of pulses in your train to reach this high efficiency regime, and we were limited by the laser source. So at first, actually, we try to do experimenting and see that we every time we get lower efficiencies compared to megahertz or even single pulse, and then there is now some really good paper from Amplitude. They just show you apply like a few pulses in the burst, then you increase number of pulses, and you have higher efficiency, and your efficiency gets higher and higher. So this is.
Okay, so I assume that it could be interesting for you to have the possibility to go above to 1,000 pulses, 500 pulses to.
Yes. This is really
okay.
Clear room for cooperation. From Italy, we go to Turkey. Seydi Yavas from Lumos Laser. What's on your mind?
Yeah, actually, I will comment on that.
Hi,
we are also working on the same regime. So we are also building femtosecond lasers with gigahertz burst, and we are now building with more than 1,000 pulses. So actually, I mean, the ablation rate is limited by, mostly by number of pulses in this regime. So with 25 pulses or so, you also observe with high energy, with high plasma shielding. So it's the reason, actually. So when you go to higher number of pulses, as also in Paulius' presentation, in bi-burst, they are also doing that. I mean, with higher number of pulses, with lower energy, you get better results. So actually, just
yes, we are waiting for your laser.
yeah.
I think the laser is coming soon. Sorry, Saidi, and thank you very much for that question. And now we go to Hamburg, and I was really looking forward to introduce the next speaker. DESY is one of the companies that, for the physicist in passion like me, it's great to hear from them. Particle accelerators put to rock. Ingmar Hartl is here to tell us about the laser role in DESY's R&D. The floor and the attention of everyone, especially mine, goes to you, Ingmar. The floor is yours.
Hello, everybody, and thank you for inviting me. Can you all hear me and see my screen?
Loud and clear and crystal clear.
Yeah. So I wanted to tell you in the next few minutes what the ultrafast laser technology can do for X-ray sources mainly. So what you see here is an aerial view of the DESY campus. We have basically electron accelerators used in the old times which were used in the old times for particle physics, but now we are completely moved to X-ray sources. And what you see here is basically a synchrotron. This is a 1 kilometer diameter electron accelerator, which is used to generate X-rays. And the next generation after synchrotrons is free electron lasers, and we have two here in DESY. We have a soft X-ray free electron laser called FLASH, and a hard X-ray free electron laser called European X-FEL. And you might have heard about the European X-FEL. This was a huge project. It's now running for a couple of years. It's a huge effort. It's a 3 kilometer long basically accelerator plus X-ray source plus experimental holes. So basically what we do, we generate X-rays, but to generate these X-rays, there's a lot of lasers needed. And this is now particularly interesting for industry, I think, because we have now finished the European X-FEL, but we have two big upgrade programs lined up. So these are the conceptual design reports, which you can download from the website from DESY. So there is an upgrade for the soft X-ray free electron laser FLASH ongoing. It's just started, and it will take the next 5 years. When this is finished, we will upgrade actually the synchrotron, which is currently Petra 3. It will become Petra 4 to a diffraction limited X-ray source. And I just want to give you a little bit insight. So we are a user facility. We are a national lab, part of the Helmholtz Society, and basically we accept proposals for using these X-ray sources. Everybody can send in a proposal, and it's for free as long as you publish the work, but sometimes industry prefers to pay for beam times, so that you also can pay for it, and then you don't need to publish. So this is ranked by typically these light sources are all overbooked, so the benefit of this work is ranked by international panels, and then typically there are many beamlines in the synchrotron. Everybody gets a few days to do his experiments, and then the next user comes in. So what is the outcome? Basically, we are in many fields. Currently, this health and life science is very prominent. So basically, just after this SARS-CoV-2 outbreak, the first people were here have had crystals on this virus or on proteins on the spike virus protein, and these were the structure of these proteins were determined by the synchrotron, and many medicine work is going on here at DESY. So my job is mainly related to free electron lasers, where ultrafast laser technology is really needed. And this is an example, basically a sketch of a free electron laser. So there is a electron gun, And the DAISY technology is a superconducting accelerator. So superconducting means you can run this at high rep rate. We run at high average powers. And then this is converted into X-rays, into undulator magnets where the electron beam wiggles around, and then the X-rays are diverted into experimental halls where our users do their experiments on multiple experimental end stations. So we have this source is given, and now I want to show you it only runs with ultrafast lasers. So what is one issue is we are in burst mode, right? And these are precisely timed bursts. So we have 800 microsecond pulses at 1 megahertz with 10 hertz beam. And we need UV lasers for generating the electrons. We need to modulate these lasers. We need to tunable UV lasers to modulate them again, to seed them. And we need very flexible lasers, which we need to reconfigure for every user, from the VUV to the terahertz, to these pump probe experiments, which are femtosecond timed to the X-rays. So we have a huge timing distribution system, which is on length stabilized fibers, which does precise femtosecond level timing of all these lasers to the X-rays. So our facility runs 24/7, so we need high reliability. We typically have more than 99% availability of all lasers during the more than 6,000 hours we run per year. And we have up to 5 kilowatt in this burst laser systems to driving this conversions. I just want to show you one example, because that's why I came to this meeting. Actually, we are, for this photocathode laser, we need flat top pulses, and we use industrial wave shapers to generate this. And what I show here in the bottom is we're also working on next generation accelerators. These are laser-driven accelerators. For these, we need kilohertz level, kilohertz rep-rate lasers with a few joule and a few tenths of femtoseconds. So these are kilowatt level, few joule laser sources. We currently have a huge program developing these lasers. Okay, so next slide is the epic question. What do we need? What do we have? So we need oscillators, fiber amplifiers, ytterbium YAG, but also 2 micro and kilowatt average green pump lasers for this electron acceleration, wavelength conversion schemes, PM fibers, fiber components, fiber Bragg ratings, pulse shaping technology, also not only temporal, but also spatial, drift stabilization, drifts in energy, pointing, timing, you name it. We need to be very precise. We need to have high damage threshold optics, which are typically dispersion engineered, typically in vacuum, which makes it even harder, and mainly for our lasers in the NIR, but our main problem are UV and mid-infrared coatings, actually, which are hard to get. We need high damage threshold components, isolators, shutters is a huge problem. We need control interface compatible to industry standards. We run remote controlled 24/7. So it's very important that our control software can interface to lasers and all diagnostics. We need high uptime, so we need to have maintenance by in-house staff and diagnostics. So what can we provide? We can give you feedback how the lasers are doing. We can jointly develop things. So if we can't buy it, we develop our own stuff. Technology transfer to industry can be done. And we can provide you with excellent stuff. For example, Francesca was at DAISY, right? So we have super people here who are looking for jobs, and they have hands-on experience. I'll show you a few examples. We developed pulse compression schemes. We developed recently low noise oscillators. This is a joint project with a company Neolace, where we did a new compression technique of picosecond lasers. And we have lots of electronics. We have precisely timed laser systems. And for this, we have even an industry collaboration lab. Plus, we have spin-offs. There are 2 laser companies funded by DESY people, which are on DESY campus and trying to sell this. This was technology developed at DESY coming out of this accelerator-driven things. And I want to give you an outlook. The city of Hamburg is basically improving this entire area where we are located, so we will have more science and more industry and more spin-offs here in Hamburg. Thanks.
Thanks a lot, Ingmar. So I guess Jose is close to cry. Such a shopping list is like what is a dream for an epic meeting. So thanks really a lot for this and for your presentation, and also for naming myself as ex-DESY Annerin. So thank you. So now I don't know where to start. So I should start with, I see some hands raised. I see some questions I want to ask. I don't know, so let's start with just laser components. So I know that we have a slide there, and she wants to talk about what can be done with optics for high power laser, right?
Yes, this is correct. Thank you for having this great meeting, and thank you for all the shopping list. So I just, laser components does laser optics, high power laser optics for a long period. And so we have the matrix that we shows pretty much the problem, I think, that you pointed out in your presentation. There's a lot of different needs, and there's a lot of different technologies. And with this matrix, we try to show you what is our knowledge and how much experience do we have. And we do have quite some good experience. In 2012, we started with a project with samples for the petawatt laser in the Bella Center, and we were really successful. And since then, we do a lot of components for this project, and I think we have a good chance to also provide some optics to you and your suppliers of the lasers. Now I don't know how to. So one thing you mentioned already is the damage threshold. So we have a lot of measured and values, not only for air, under air, we also measured already with under vacuum. So we do have all these values for picosecond, femtosecond pulses, and I think we have quite good results there.
Yeah, do we have we have burst mode lasers, and this is lasers other people try to use for materials processing, and it turns out the damage threshold is much lower. So we actually did a big effort to measure the damage threshold ourselves, and we also need dispersion engineered mirrors, which are typically lower damage threshold. And what turns out is the most critical thing is we need also metallic coating with dielectric overcoating for broadband, and these are turns out also to be very hard to manufacture mirrors for high damage threshold and also for environmental vacuum conditions.
Okay, so that's we have to maybe discuss extra.
We need metallic substrates. If mirrors are in electron beam, they need to be conducting substrates that they don't charge up. So we have huge demands on.
Okay, so that's nothing we do yet, but especially for this petawatt project, just to explain you, we bought a chamber in order to have large optics for this petawatt project, and we so it's really the investment was for this project, and we use this now since 2015, and so we are open to also do, maybe we have to discuss, we have to find out.
So you're doing IBS coatings basically, right?
Also, ion assisted.
Yeah, so we mainly use IBS coated.
Yeah, so we just ordered a new IBS chamber for larger components also that will be delivered this year. So there's a lot of investment on new products also, so we are open to discuss this.
Great.
So just to give you...
Yeah.
Sorry.
Yeah, you want to add something? Yeah, sure.
Yeah, just to give you an idea what we did for this petawatt project to understand what is, I mean, we really do custom specific. So we did this for 300 by 200 millimeter components, optics, and gutter flatness. After coating, that's another topic. You have hundreds of optics, and it's a problem if they bend, and the IBS is bending, but we reached a lambda over 8 after the coating, which is quite a good for this size result, we think. And sorry. So this is the chamber that I just said. This is the chamber really we bought for this.
So so you want to share the screen because you're not sharing it at the moment.
Ah, I'm not sharing.
No, no. So there's the green button below. If you, because I was not sure if you had the slide already or not, but if you want to share, there is exactly now she's coming.
Okay, so sorry.
Very good.
So this is the chamber that we have bought, and it's specifically made to have a good homogeneity, because that's another topic, to get a good homogeneity on large optics. And so how do we measure it? We do a special coating on the filter, coating, and we look specifically in the slope here and see that we get, for example, less than 1% in differences. So this is really, we did develop all of this for this customer, for this petawatt laser applications, and we delivered now many optics, and I think we are very open for new projects, and this is what we can do to you.
Very good, thanks a lot. So I guess we have to move on because we have so many questions. And I know that Ralph from 26 doesn't have only a question, but he can show you what he did for Ingmar, and also can be done for you as well, right? So ex-finis are now 26. Ralph maybe can share his screen. Now we can, so this one, we remove this one. And now Ralph, are you there? Yes, I see you. Welcome. So you are already a big buddy of Ingmar, right? Let's say, let's find you some new friends here as well.
Yes, thank you very much for giving me the chance to quickly talk about our activities. And I would like to pick up on the wave shaper, which Ingmar has mentioned. So the 2.6 wave shaper is a programmable optical filter. It comes in a box, benchtop box like this, or it also comes in a module, which you can integrate in laser systems. And the type of applications we are following with this wave shaper is we can do shaping of femto and picosecond pulses, shaping of the pulses in the time domain. So we can do, for example, pulse compression, pulse stretching. We can create special pulses like double pulses or rectangular pulses. And other applications are spectral broadening of a laser line by applying an M-shaped filter. And also what we can do is we can create wavelength tunable pulse lasers. So these type of applications can be addressed with this programmable filter, which is based on liquid crystal technology. It's a spatial light modulator. That technology is broadly used in telecom applications. So there are hundreds of thousands of these devices in telecom networks. And now in this conference, as we speak, I'm sure we are using several hundred of those devices along the lines. The key characteristics which we have here, that's we can provide arbitrary spectral shapes in attenuation and in phase, and all that is delivered in the 1 micrometer window and also in the C band and the L band. We have a fine resolution and we have a fast update rate of faster than 1 second, and this is all done with PM fibers. So now to give you a better idea what you can achieve, I have an example here. And this example shows you the spectrum of a mode-locked fiber laser where we do not apply our shaping, no filtering applied. And this mode-locked fiber laser here has a length of about 1 picosecond. And now with applying the proper filtering, with the wave shaper. So we first apply an M-shaped filter so that we depress this single narrow peak here, so that in total we get a wider spectrum of 8 nanometers instead of 5 nanometers. And also we apply some phase function. This green phase function causes a flattening of the phase. And as a result, we get a very clean pulse of only 300 femtoseconds instead of 1000 femtoseconds. So this is just one example. This is programmable from filters from any computing environment, and so you can just run your own filter shapes the way you like.
Very good, Ralph. I was muted. Sorry. Sometimes I do the mistake as well. Thanks a lot, Ralph, for this. His example is always helping. So if you get a 3 times better pulse, of course, that's the right place to put your beam shaper. Thanks a lot. So now we go to the questions. Sorry for waiting. Today is crazy. You are amazing. You are asking so many questions. So now it's time for Christoph from Thales Lasers. It's great to have you here. You have your hand raised. So please ask your question or comment.
Yes, thank you. Thank you, Ingmar, for the very nice talk. I have a question. Can you say a few words about the progress of the kilowatt laser project?
Yeah, we have multiple kilowatt laser project. We have ytterbium YAG kilowatt for free electron lasers, and we have for laser plasma acceleration kilowatt TATA laser project. And basically,
I was talking about the Caldera project for laser plasma acceleration.
Yeah, the Caldera project. Yeah, it's in progress. It's just started. It's a long-term project, and what I can say is that laser plasma acceleration is long time around, and it's unfortunately not real yet, right? So no free electron laser was driven by a laser plasma accelerator, but we are close here. So what we see, the main drawback is all these conventional RF driven accelerators run at megahertz rates, right? And superconducting run at there are a couple of superconducting accelerators around the world now, and laser plasma accelerators used to run at 1 hertz, maximum 5 hertz, maybe because of these Joule class ultrafast laser not being capable of higher repetition rate. And what we want to do in this project, we want to do the breakthrough to make this a real world source. And what's also an issue is reliability. So as I can't stress more, we might have only one or a few lasers, but we need them to drive a $1 billion accelerator. So if our gun laser dies, the entire facility is down. So we need reliable, and so that's why I like Ralph's telecom stuff. Telecom stuff seems to be much more reliable than the rest of ultrafast laser technology. We have huge issues, for example, with our mod-locked oscillators. When they die, it's really an issue. So they don't die often, but if they die, a facility is down. So we need the reliability, and this also needs to transfer to the petawatt lasers.
Thank you.
Thanks a lot. Thanks a lot for the questions and the answers. So now it's time for Cliff from PI. You have also your hand raised.
Hi there.
Hi.
Yes, quick question, Ingmar. So I come from a motion control automation background. So when we were dealing with the research institutes such as DESI, they were always interested in, from one of your points, the control interface, which was always typically Tango or another EPIC. Is that what you're referring to? Are you referring to those types of control interfaces, or are you talking about more industrial interfaces such as EtherCAT? And if that is the case, do you expect, say, for example, the laser manufacturers to be able to provide those types of interfaces?
Yes, and I'm not talking on Tango. These systems are used for synchrotrons. They don't have the capability of timing. We need to timestamp each of our pulse, which runs at the megahertz. And we developed our own control system. It's called Dukes. You can look it up, which is basically running on this micro TCA hardware, which is a telecom standard developed, comes from telecom standard. It's a FPGA driven stuff, fairly complicated, but it has interfaces to industry standards. So we like, for slow controls, we like OPC UA, for example. For fast controls, we can do CAN bus, we can do RS-232, of course. What we can't deal with is a Windows APE, because our system this is a Linux system, and we like to have standardized interfaces, which we can do. We run with PLCs with OPC UA. All the fast controls are actually directly driven by the FPGAs, either through DUCs and ADCs or direct digital controls.
Thank you.
Yeah.
Very good. So this was a needed explanation. Very good that we can detail it here already live. And now it's time for Tobias from Gentech, right?
Yes,
welcome. There you are. Welcome. Thank you.
So yeah, Tobias with Gentech Electro Optics. We provide power energy meters, profilers, cover the region from UV all the way up to terahertz, and can measure pulse-to-pulse energies, up to into the kilohertz region. So I'm curious, Ingmar, in your slide you mentioned drift stabilization, and I'm wondering, do you have a target for energy stability of your system, or any limitations currently in that area?
So for gun lasers, we need to be 0.1% pulse-to-pulse energy stable for our electron sources. For seeding, it's more like 1%, but this is a tunable UV system on an OPC optical parametric conversion scheme. So this is really challenging. Wavelength stability also 1% on the ultrafast. 1% of center wavelengths on ultrafast things. So it depends a little bit on the application. So at the end, timing stability is extreme. We need femtosecond level timing stability. So we need to deal with all this. We have length stabilized fibers, and we need to deal with all the environmental changes. So for example, I can show in the European X-FEL, we see the tidal motion of the Earth crust, because it is a 3-kilometer accelerator, and we see this in our timing system. We see this period from the Earth expanding and contracting. So at this level, we need. Of course, this is predictable, so that's easy to feedback control, but there are other things which are not so easy to feedback control. So.
Very good. Yeah,
Very good. Thanks a lot. So thanks a lot, Ingmar. This was really a nice presentation and really nice answered questions that you gave. So we hope that we can put you in contact with all the people that I'm sure will want to talk to you, maybe also in private. So thanks a lot. Let me add that the two spin-offs that you mentioned, we can say now finally they are both EPIC members, so Cycle and Class 5 Photonics. So they are also here in the room. So that's a very good signal of how close we are to Daisy already. So thanks a lot. And now talking about the optics, your issue, you said, so we need really stronger optics for high energy and high power in general. So it's time now to tell the experience that HiLase has in this, and also the service that they have. So that it's time for Daniela to start their presentation, because the floor is yours, Daniela.
I hope you see my presentation.
We see the right screen. Perfect. There you go.
Francesca, I'm really glad that today we had a lot of questions about optics, because this is making me feeling that we are not alone there. My name is Daniela Rostocker, and I'm going to speak about laser-induced damage threshold measurement at HiLase. For you who doesn't know what is the HiLase, this is the laser technology R&D infrastructure, which is located nearby Prague in Czech Republic. We usually like to say that we have under one roof together laser development and application development. If we're speaking about the laser, we are developing new generation of diode pump solid-state lasers, and we are working on two technologies. One is cryogenically cooled slab systems. You probably heard maybe name of a BVOY laser, which are delivering 100 joule per pulse in 10 nanosecond pulses. Or maybe you heard the name Perla, which stands for our line of diode pump millijoule thin disk lasers, which are giving pulses of less than 2 picoseconds. Yes, we also do application, as I said. We are doing laser shock peening, also laser micromachining. I'm asking our first speaker and others to look what we are doing for laser micromachining with the approach which is called multi-beam processing. Just short, we able to drill simultaneously over 700 holes. And most my talk today will go on laser-induced damage threshold. What is that? Once you start really developing complex things like high-res lasers or DESI, you will very soon see that you have something what is limiting you, and this is laser-induced damage threshold. Or in other words, you will start seeing a damage on your optics. Damage of the optics is given by so-called LADT value. Basically, you will gonna to get some kind of graph like that showing the damage probability for certain fluency. And we say that we are safe in this blue region. But if we go to a little bit more back to the physics, fluence, it's related between energy per pulse and spot size. That means you can basically work in two regimes to get same fluence by low energy per pulse and small spot, or high energy per pulse and big spot. That means if you are looking for optics and somebody tests your optics in this first regime, and you're gonna to use it in your another regime, like the second one, you will see huge difference. Your optics is gonna to be damaged on much lower fluencies. That means that it's very important that you do testing on the this second regime. Down you have just few pictures. This is our setup. This is how it's usually looking, the testing, and some surprise, you see the damage on your optics, which was tested and supposed to work for you. And coming to favorite question, what we can do? In order to test our optics, we start LADT, and now we can offer as a service as well. That means we can do a standard ISO standard testing on different size of samples and up to 1.5 kilo in weight. Also, we do in different conditions. I saw that today was interesting in the vacuum. We also very soon will have testing in cryo temperatures. But what is really important is that we are providing this kind of testing under this second regime. That means we have a millijoule energy pulses in picosecond and the joule level in the nanosecond. And the second question, what you can do for us, helping us to reduce the cost in optics and coatings, and also helping us to reduce the waste of the time. That means you can jointly working with us in understanding which kind of defects are influencing on LIDT. Then also jointly with us develop new coatings and do analysis, and of course testing your optics in these specific kind of regimes. I'm just asking you to follow us on our social medias, and you can see more information about all of that. And that would be all from my side.
Thank you very much, Daniela, for once again a great presentation and also looking always to collaborate. I have to say that so many companies are following up in different introductions that we are making to HiLace, and I keep getting great feedback from collaborating with HiLace. So congratulations on the great job that you are doing. I would like to ask always companies who can interact with HiLace when it comes to measuring the LIDT. So let's go to a company in the optics domain. Let me think, Asphericon. Do we have anybody from Asphericon? I think we do. Sabrina, I don't think I met you before, but Sabrina, thank you very much for being at this meeting. Sabrina, one question. We are talking here about potential collaboration for the measurement of the laser-induced damage threshold. How does Asphericon deal with this? And is there perhaps some room for cooperation?
I already put a note down for myself that this is something that is so important, and it's always recalled from customers that they want to know exactly the laser damage threshold. We don't measure this in-house because we don't have the option to measure this. We don't have all the lasers, but we can do optics for high power laser applications, and we can do coatings. And I already put a note down, Daniela, that my coworker who would be responsible for your territory, that he should get in contact with you again, so that we can find a good way of cooperation, because you offered that you can do the laser damage thresholds as well. So we could do a cooperation in that way, that you do the laser damage threshold measurements and we do the coding, do the codings and do the optic developments.
I just would like to say that for us, probably one of the biggest costs is getting the optics which is not working for us. And I'm expecting that the DESI will be in the same problem like we. And this is why I was pushing a little bit Francesca to put up this topic, because it's not only cost of the optics, but also the time. Because you get a huge amount of optics and then optics doesn't work for you.
I want to find you. Sorry, Sabrina, go ahead.
Yeah, I truly see the point that what you want, but as of today, we can't do the tests, but you can only do the tests and we can do the optics. So it would always be like playing back and forth, and there will always be some optics lost in this whole testing. So
yeah, but
it's a development, and we are so close to you. So it's definitely worth it. I already put it on my agenda here.
I'm here to close gaps always, Sabrina, Daniela. So I'm going to go to maybe a company that can help with this. So I'm going to go to Imaging Optic. And the reason why I go to Imaging Optic is because I went to visit them in Palaiso and I loved it. I loved the food and I loved the tour, but I also loved the way that they are working with the characterization of optics with the wavefront sensors. Do you see the presentation from HiLace? Is there a potential room for cooperation, Martin?
Yes, hello everybody. Yes, for sure we are managing the beam, the wavefront beam measurements, of course. But the main thing that we are also providing some deformable mirrors, that we have the same question about LIDT of the coatings we are providing. It's always a question of experience, maybe at the time, because we have some providers for the coatings, and it's also a challenge on that. Because the lasers are higher and higher power actually, and we know that it's always a question. But characterization of the laser beam, exactly, we have the tooling for that. The wavefront sensors help us a lot on that, and conjugation in a loop with the deformable mirrors is also a good solution to have a beam shape and to make the best beam. The beam shape on the target, so you have the threshold. Maybe the laser threshold damage could be a bit different if the beam shape is better.
Marshall, thank you very much. Daniela, be prepared to a long set of introductions that I'm sure are going to happen after this presentation. And I'm going to move on to the next speaker. And those of you already know me a bit that know that the next presentation is something that I always look up to. Fluence. Thank you very much. Shenkubie Parcho for being with us this afternoon. Happy New Year. Let's go to the high power, ultra fast lasers of Fluence. I'm a huge fan of this company. I can't hide it. Welcome. The floor is yours.
Okay, thank you very much, Jose.
I understand you hear me loud and clear.
Loud and clear.
Okay, good. Let me share the presentation.
It's always difficult to combine the high power and the ultra fast as these guys can do, and especially with the well below 250 femtoseconds and the 30 watts, it's really, really unique what these guys have in their hands.
Yes. So thank you very much for opportunity, and thank you very much for interesting talks you all have today. I'm very amazed with how many questions there are. So it's really one of the better talks I'm attending right now. So just to give you a rough idea what Fluence does. So we are a company from Warsaw, from Poland, that was founded about 5 years ago. And then we base on a long experience that we got from Polish academic institutions developing lasers. So we developed lasers basically from 2003, so it's already a pretty long time, and it helped us in constructing this nice all-fiber lasers with very good parameters that are reliable and have very good optical parameters. So just to give you the overview, we at the moment have, we focus on 1030 nanometers, and we have a range of products from very small seeders of 20 milliwatts up to lasers like Jasper, which goes up to 60 watts. And this is, I think, the most interesting laser to talk about during this meeting, as I see everyone here loves high powers, which is great because we can provide high powers at femtoseconds, not as high as kilowatts, but still amazing for what femtosecond lasers and fiber lasers can do. So just to introduce, Jasper laser is a fiber construction that was developed on a very special oscillator where we don't use cesium, and as much as possible is confined inside the fiber, which means that you can get very good pulse stability and very good pulse quality. Of course, this led us not only to provide laser power at 1030, but we can also generate second, third, and fourth harmonic, which are more and more popular in micromachining nowadays. This is one picture for what we can do. So here you can see we fourth harmonic and second harmonic generated. But also a very nice effect you can see in this piece of silica in the bottom left corner, shows you that we have very nice high light intensities that generate this excitation effects, which means that we can reach very, very high peak powers. Just to give you like this is to show you what nice things we can do apart from what we offer. We built this laser that goes up to 100 watts. I understand this is not a lot for people who deal with kilowatt lasers and higher, but talking about fiber laser with very high tunable repetition rate, very good m², very good strahl ratio. This is really amazing result, especially that you obtain 200 femtosecond. We obtain 200 femtoseconds at the laser output. Of course, having this kind of lasers, we also run an application lab in Warsaw where we could develop all these different we could check different applications like super hydrophobic structures, material processing, glass cutting, and more interesting applications that we are happy to test. So this is actually answer to the question what EPIC members can do for us. So we are still looking for new applications. We are looking for partners who want to collaborate and who want to not only test our lasers, but who have like nice ideas of how this high power femtosecond lasers can be used. And we can provide some help in this field, especially that we are now opening a new application lab in Wrocław, the southwest of Poland, where we will have very nice equipment and just dedicated team to run this kind of applications. So thank you very much. That was, I hope, quick enough, so we have time for questions.
Yes, it was enough, and it was really nice as usual. Darius, thanks a lot. So yeah, it's true. So we have many questions today. Did you see it? Yesterday I heard 3 times a question like, how do you feel 2 hours with only short 6 minutes talks like this, like we see it today. So you said, so you have your shopping list. You propose it so a bit ideally, so you don't really have a shopping list. So you ask for applications. So can you maybe tell what is the sector? So where is it that you would like to a bit more investigate in? Where is the use for a fluence laser?
Applications are mainly in micromachining, so in laser processing in general. So having these high power lasers nowadays, it is important to mention that well, what is important is that having this much power and energy in a single pulse, it's actually too much for most applications, right? Because optimal fluence for most materials is low enough that you only require between 3 and 11 microjoules. So it means that it is necessary to find a way of splitting this power, of like reorganizing the way we do micromachining. So one solution is that we use beam shaping, like Marshall just said before me, and do larger areas at one time. And second thing is using higher repetition rates. So you have more pulses in the same time, and then using very fast, for example, polygon scanners to increase the process speeds. So these are areas we are for sure very much interested into to look into.
Oh yeah, so scanners, laser scanners, we have a really nice connection in Ibek, so that's something that we can help you with, of course. And with the application, just let me know. We can also put it, if the people here are shy, or anyway, if you need to talk with some system integrators, we will help you, definitely. And now let me move to Nico from Jenoptik. You ask a question in the chat, maybe you can ask it yourself.
Yes, so thanks for the presentation. There's only one question that I would have, is about the beam size coming out of the laser. So in parallel, I was looking on your website and I could not find how large is the beam coming out of your source. Do you have any information on that?
Well, it is usually around 4 millimeters diameter. Right. So, but this is always a question. I mean, you can define it yourself what you want, right? It's not difficult to change the beam diameter.
No, of course we can make it bigger or smaller, but it's necessary for us to know how big it comes out. And so, but how about the tolerances? Is it like a 5 or 10% tolerance of the beam size, or how stable are those systems?
I mean, when it comes to beam size, the tolerances are very, very good. So especially that, well, our laser, it is based on fibers, and as you know, fibers are very good Gaussian filters. So well, it is definitely. I don't have a number in mind, but I can definitely check it and well, let you know after the meeting.
Sure, thank you.
Now, Darius, another question. So do you have some issues with thermal management so far in building up your lasers?
That's a very, very good question you're asking, actually, because the reason why we built this laser is to avoid this thermal issues and thermal effects, right? So we have this oscillator, which is amazing, and we test it from like -10 degrees to 40 degrees Celsius. And as it is running, nice and stable. So so of course the bigger system you build, it gets more complicated and more components are prone to temperature changes. But the thing is that the oscillator is still the most important part of the system, because this is where the pulses are defined. So well, we believe we are pretty good compared to other laser manufacturers when it comes to
very good, Darius.
thermal stability.
That means that you maybe don't need, or maybe you don't know yet, because you never know if in the future maybe something comes up. But other laser manufacturers maybe would like to talk with Joanna, right, from Mintres, because she has actually solutions for thermal management, right?
Hi.
Hi.
Hi, everybody. Thank you, Francesca and Jose. Yes, so everybody is doing a great job, and also thank you so much for great lectures. It was very interesting for me. So our company is specialized in thermal management, and especially high power lasers and that kind of applications. So I must say we do have few special solutions, but of course, like life is always complicated. We also still working on advancing in that. So we also always looking for additional partners, trying to get even better with our different prototypes or production lines we have. So just brief overview, and more related to today's topic, because we do have several business lines in our company. So one of our stories is thermal management, and in case of like high power lasers, we specifically focus on the overheated parts, so heat source and hotspots. So for that, typically everybody has such a different design that we start usually with some prototyping, maybe R&D. If solution is interesting, we are capable of producing those components. So these are always custom-made components, because yeah, the designs are varying so significantly that many solutions can have similarities, but it always have to be reiterated. What we do are heat spreaders, heat sinks, could be micro coolers, and this is all based on ceramics or synthetic diamond. And I hope most of you already know that diamond is the most efficient in removing the heat. So there are also other cheaper options, of course. Aluminum nitride, for instance, is one of our top choices. I would like to also mention, which could be interesting for quite a few people in the audience, optics. We also specializing in a very specific made of diamond optics, and that could be optical windows. There are detectors, sensors, beam positioning, and especially in synchrotron radiation, infrared applications as well. So we are quite diverse, and we exist already 13 years, but our key people have like life experience of 30 years plus in those subjects. So if anybody have any questions and troubles, probably our team already was dealing with that before. So thank you so much for allowing me to share a little bit on Mintres.
Of course, Joanna, we are here for you also in this way. So thank you very much for also presenting you and also joining very recently EPIC. So very welcome. And we look forward to connect you with the many possible collaborators and customers for new projects. So really welcome. So if I don't see further questions, I mean, we would have many questions in the chat. I saw, I mean, you were really amazing today, but maybe we go to the next speaker and then we keep a few minutes afterwards to have maybe a big discussion with you and also with the other people that maybe didn't speak yet. And now we give the floor to Joachim from Pulsar Photonics. So now we met him already earlier in the meeting, and now he will show you a bit what his company is doing in Aachen.
Hello, everyone.
Hello, Joachim. Are you still there? Very good. Yeah,
Yeah,
I see
I'm
you.
here.
There you are. There are so many people. I have to catch where you are showing up. Please share your screen, and the floor is yours.
Yeah. Thank you very much for the introduction. Do you see my screen? Do you hear me?
Yes, but we see either the wrong one. Oh no, you're not yet in presentation. Yeah, now perfect. Yeah, there you go.
Yeah.
Thank you.
Okay, you're welcome. So, hello, everyone. At first, give me the possibility to introduce our company. Our company, Pozo Photonics, is focused on ultrafast laser micromachining. So this topic is quite good for us. What we do is laser material processing. So it's more the production side of the applications. Our company is founded in 2013. Two colleagues and my in personal, we founded this company as we now are each other from the Fraunhofer Institute of Laser Technology in Aachen. Actually, we have 40 employees, and we are located in Hartl and we have distributions in Asia because this is one area that drives the system technologies as we see. So here you can see the distribution. Actually, we are here in the technology park, it's called, in Hartl. There are a lot of laser companies, a lot of spin-offs coming out of laser institutes, and yeah, this is the way you can find us. Furthermore, you can find us also in the web. Actually, in the next day, we will relaunch our website, so we're invited to have a look there, and of course to contact us if it's interesting for us. Yeah, what we are doing, we have 3 business units, and the first one is about laser processing. Where do we come from? It's about the development of processes to have know-how. What we're doing, it's about the responsibility that the processes are working. We run our own application center with several machines of our own machines. And what we're doing there is also contract manufacturing. So we know the production side of ultrafast laser processes and all the stuff, problems, experiences that come out of these questions. Yeah. The second business unit is advanced optical systems. That is the point where we initially come from. It's about industrial beam shaping systems. We are very familiar with diffractive optical elements, with beam splitting, with setting up scanning systems, being able to scan hundreds of spatial beams. We develop customized light engines, also with spatial light modulators. And we put it all together in a running system, in a running machine, so it can be really applied to processes. It's mostly ablation processes, it's drilling processes, it's structuring, surface functionalization, and not that often it's cutting processes, and all these beam shaping,
Joachim, we hear you a bit. Yeah, now you get better. We heard you. Yeah, so please, the microphone, I don't know what you are doing, but it was very, very quiet at some point. And now it's working better. Well,
okay, fine. And all of them has something to do with the integrated metrology. We have to care a lot of the beam pointing and the beam stability, also of the laser sources, because this has a strong effect on the shape of the beam distribution. And our third business unit is a machine. So what we do there, we of course design the machines and set them up. We do the assembly and
again the same issue.
Machine stages. Yeah.
Okay. Now it's working again. Maybe It's not cabled, right? Your microphone and headset. Yeah, maybe the battery is getting down. Okay, but I let you then speak before we are completely off.
I come closer to the mic.
Okay.
And of course, yeah, that has to be set up in the machine. And now I'd like to give you a small overview of to the application that we are busy with. So of course it's tooling. The tools are becoming big and bigger, and they need more laser power. Of course, if you think about hardened coatings on it, we have to do a lot with friction reduction or with enhancing or tailored friction parts. What we're doing is a fine metal mask and sieves, very precise applications with tolerances down to a few microns. Security markings, here you can see one application that we did together with the IWS with Tim in Dresden. So it's we are familiar with adopting also systems and optical systems that are not developed by our own. Glass processing is a small part, not our main part. So it's more coming to that part, to the filter devices, electronics, and ceramic production. Here, if the parts are becoming larger and larger, we need a lot more laser power. Yeah, coming to the last part, where you can see here on our right-hand side, beam distributions, digital ones that we can produce with our system and apply them to different processes. This is one approach that we see, tailored photonic tools, if you want so. These are the four main drives that we see. We see that beam shaping is one of the key technologies to solve it, to solve the conflict, to achieve high qualities, and yeah, to enlarge the throughput, or to make it possible that we can process larger tools. On the right hand side, I've seen some distributions, and we are one of the few companies that develop these systems. Macro application is upcoming. I see we see a lot of reel-to-reel applications where we need high laser powers to put the power on the blanket. At the beginning we saw this nice application from Pieter. That is a good one. Here you can see a system will be delivered. It's more than 150 watts on average. That is actually the high power range in laser material processing. I know that there is much more available, but actually we are dealing with 100 watts plus to put that in the material microprocessing. And yeah, what do we need from there? We need high laser pulse energies to enable the beam splitting, but also if we think about drilling of larger material thicknesses to process materials with high aspect ratios, we need pulse energies in the range of several hundred microjoules or millijoules. And high speed motion is also asking for higher frequencies, pulse frequencies, and at the end in high average powers. The third one is a very specific topic because I guess actually it's a national German topic. We have strong regulations regarding X-ray protection and also nanoparticle emissions. These X-ray emissions come out if you exceed specific fluence on the workpiece, and you easily run there if you use femtoseconds, but also high power picoseconds and small focal diameter will lead to these X-ray emissions, and these are known as dangerous for the operators. And to be able to apply multi-kilowatt ultra-fast laser processes in a safe environment will be a large topic, and I guess that is, you cannot put it from the agenda, that will spread out worldwide and everyone has to tackle these problems. This appears. Nanoparticle emission, also quite important for the operator and the machine builders. If you apply such huge laser powers, all these particles will appear and not disappear, so you have to apply suction exhausting technologies that are capable to reduce or to zero these particles. We heard a lot of optical thresholds and what's demanding for us. If you put 1 kilowatt or more to a beam delivery system, it has to be really clean. It has to be really clean in production environment, and this is also a topic everyone is invited to help us, to assist us, and to give solutions for that. And the fourth is actually, we know that there are a lot of fiber-guided beam deliveries on the market. I don't know if there are some available in the range of several hundred microjoules pulse energy. We wait for them because it makes it much more easier to apply it in the machine, and this will be the enabler if for the large machining operation. If you think about toolings, very large, very expensive, and you want to guide the ultra-fast laser beam along these stages, it's quite demanding, and actually all robotic operations are quite difficult if you use free beam delivery. Yeah?
I love when Joachim comes to this meeting and he comes with his shopping list and so many potential collaborations going. It was really, really great. By the way, I love Pulsar and I already own you a visit, a long overdue visit. I want to come to visit you. But first, I want to find you potential partners. So I'm going to go to France because I have a friend at Alphanov. Johan,
yes,
what did you have in mind for Pulsar Photonics?
Yeah. I was impressed by what you presented, and because you give the big picture where we are on the ultra-fast technology. I have a particular focus on the fiber-guided beam delivery. I would like to know your opinion as an integrator and a machine manufacturer on the impact of this kind of technology. I think to ultra-short pulse delivery by hollow core fibers, for example, from photonic tools, the impact on the price of the sources, maybe a few comments on the maturity of the technology. What's your opinion on this and on its impact on the market? Because this is something that we are talking about since now five years, and this is not yet on the market, and I would like to have your opinion.
Yeah. Okay. Maybe we start with the maturity price from the last thing. So we are following this topic since since the beginning, right? Because we come from the institute since 2007, 8, stuff like this. The price is dropping. Yes, it's correct. But the latest sources itself are not really cheaper, because if of course the source itself comes.
Joachim, the bandwidth is complaining now a little bit.
Yeah,
So, but
okay.
I do see room for cooperation here. So I'm going to make an email introduction and also highlight that I am happy to introduce anybody to each other. So just send me an email if you want to be introduced to any of the other participants. But I want to go now to Berlin. I want to go to a company called FineTech. Ralph, it has been a great meeting, and I have seen FineTech machines at many of these locations when I went to visit them. What room for cooperation have you seen during the last 2 hours?
Actually, I have seen that a lot of the companies that are there are using lasers, and we could help some of them if they are in the area of diode laser or laser diode packaging, or if they have some difficulties there or so, or if they would like to start like R&D programs on diode lasers, and we could help them with process know-how, or with machines, or with toolings, or also with networking for such activities.
I've seen your machine at work at the Prima group on the high volume passive alignment of the laser diodes, and it's super impressive the high speed assembly that you can achieve. It's an honor to have you on EPIC.
That is one thing, and as you see in the image that I just share on the screen, we go really from prototyping, from R&D phase up to volume production. Yes.
And I want to go now from Berlin. I want to go to Hannover, Rock City. I want to go to Valo Innovation, because it's one of the companies who has something fantastic in their hands. Oliver, we had a nice meeting. There's many companies here. You are in the lower power, ultra short pulse, 20 to 40 femtosecond. What opportunities for collaboration? What ideas do you have after this meeting?
Yeah, and thanks for all the talks. Yeah, let's say Valo Innovation is just focusing on very short pulse for, let's say, some kind of mainly at the moment it's biophotonics, but also micromachining in the future. Could be a very good topic. And yeah, the question for me would be if there's somebody who's interested in having really short pulses, and yeah, that would be interesting.
We had a question in the group, in the chat about the market. I do foresee the microscopy market to grow quite a bit in the coming years, and the ultra short pulses are something that we are desperately looking at. But answering this, I want to give the final remark to IPG, because it's the market leader. So who am I to talk about market? Michael Lee, thank you very much for being with us today. What are your final remark? What do you keep in your head after this meeting?
Thank you, Jose, for the opportunity. So it was an interesting meeting to talk to all of you, some customers, friends, and experts of the industry. So what I initiated in the chat in parallel, as I heard from Joachim, they are waiting for hundreds of microjoule industrial lasers. And we, as an elephant of the industry, we are waiting for the market for. So somehow we have to come together on that, saying, yeah, there are single quantities here and there, but we would like to understand and develop the overall market sizes with you together. And this is something what I take as an opportunity, and I had live chats in parallel. So stay tuned. We will come together soon.
It has been a truly great meeting. For me, the learnings are first. We got TATA still telling us a huge challenge. And we got Desi with the most beautiful shopping list I have seen in a long time. We also have great room for cooperation with the ultra-short pulse characterization of APE, the ceramics from Mintres for thermal management, the laser-induced threshold measurement from high-lace, the high-power ultra-short pulse combination, and Goosebump generator for me, Fluence in Poland. It has been a truly great meeting, but it starts now with the cooperation, because at the end of the day, it is all about cooperating, finding this room for cooperation. This was the 60 EPIC Online Technology Meeting, and we will continue. You know, soon we are all going to be vaccinated, but doesn't matter. We discovered that the online way of connecting companies also works. We are going to organize every week at least one or even two online technology meetings. So please stay tuned and have a look at the calendar that is already published in the website. But the most important is, when the meeting is finished, the work starts. If you want to get in touch with any of the participants today, all you have to do, send me an email, jose.pozo@epic-asoc.com, and me or the rest of the fantastic EPIC team, 15 people, 7 PhDs looking to understand the technologies, a fantastic validation manager, a fantastic marketing manager, a fantastic innovation manager, and behind the whole adventure, Carlos Lee, the Carlos Lee of EPIC. Thank you very much for being with all of us. Stay tuned for the upcoming meetings, and for anything you need, the EPIC staff is here for you. Until the very next time, from North Pike, the Netherlands, to the world, that was Jose Pozo and Francesca Moglia. Take care. Bye-bye.